So hello everyone and welcome to today's video where we will be exploring the UART protocol, a fundamental communication method used in countless electronic devices and microcontrollers. I am excited to take you through this journey of understanding one of the most widely used serial communication protocols. I won't be diving too deep into the technical details as my goal today is to provide you with a clear basic understanding of UART protocol and that you can build upon later. So now, today we are diving into UART, so which stands for Universal Asynchronous Receiver and Transmitter. So you might be wonder why it's called universal. Well, that's because its parameters such as speed, data size, and other configurations are not fixed and can be adjusted based on your specific needs. So UART is specifically designed for asynchronous serial communication. Unlike synchronous protocols, UART doesn't require a clock signal to be transmitted alongside the data. This takes it simpler in some ways, but also introduces some interesting challenges that we will explore throughout this video. Let's move on to understand one of the most important aspects of UART communication, the baud rate. So, the baud rate is essentially a measure of the speed of data transfer expressed as symbols per second. In most contexts, it's represented by bits per second or BPS. To put it simply, the bit rate refers to the number of bits that can be transferred every second. Okay, so when working with UART devices, so you will commonly encounter the standard baud rates like 9600, 4800, 19200, 38400, and many more. These standardized rates ensure compatibility across different devices. An interesting thing about UART is that generally the baud rate and bit rate are the same, having a one-to-one relationship. This is because typically UART uses one bit to represent one symbol. So unlike other protocols where a single symbol might represent multiple bits. So now coming to the part of the synchronization. So before going to the topic synchronization in UART, so let us recap what happens in clock-based synchronization. So you might have learned about the clock-based synchronization where the incoming data bit is sampled in the active edge of the clock, like active postage of the clock, or it might be neg edge of the clock. So it happens simultaneously to the both inputs like QA or QB. They are both synchronized on the basis of the clock. Okay, so now coming to the part of synchronization in UART. So since UART is asynchronous, meaning there's no separate clock signal. So now the question might arise, how do devices know when data transmission begins or ends? So this is where synchronization comes in. Every data frame in UART begins with what we call as a start bit, which is always a logic 0. This falling edge from the ideal state signal the receiver that data transmission is about to begin. For UART communication to work properly, both the transmitter and receiver must be configured to the same baud rate. So common rate includes 9600 or 1,15,200 BPS. Okay, so BPS bits per second. So many other exist. We can use commonly 9600. Okay, so if the rates don't match, the receiver won't sample the bits at the correct times, resulting in garbled data. So data might corrupt in this case. Okay, so after all data bits are transmitted, one or more stop bits here represent with logic 1 are sent to mark the end of the data frame. Okay, so when no data is being transmitted, the line remains in an ideal state, which is high, logic 1 in this case. Okay, so there's also an optional parity bit. While not strictly for synchronization, it helps detect transmission errors by ensuring the total number of ones in the data, including the parity bit, is either even or odd depending on the configuration. Okay, so now moving to the next part of UART communication. So UART communication can operate in 3 different modes. So first is simplex mode, which allows data to flow in only one direction from the transmitter to the receiver. So the next mode is half duplex mode. So half duplex means device can both transmit and receive, but they must take turns. They can't do both simultaneously. So and the third one is full duplex mode. The most versatile option allows devices to send and receive data at the same time. So what makes UART so flexible is that both the data format and transmission speeds are configurable based on your specific UART. So the actual communication happens through the two independent lines or wires, the TX for transmission and RX for reception. When connecting two UART devices, the TX of one device connects to the RX of the other and vice versa, creating a crossover connection. Okay. So now moving to the next part, the data framing part. So here we will see the data frame of the UART which is sent from transmitter to the UART side, UART receiver side. Okay, so let's look more closely at how data is framed in UART communication. So when no data is being sent, the UART transmission line is held at a high voltage level. This is the ideal state I mentioned earlier. Okay, so the actual information is carried in the data frame, which typically consists of a 5 to 8 bits. If a parity bit is used, the data frame can be 5 to 8 bits, otherwise it can extend to 9 bits. Optional parity bit is used for basic error detection during transmission. There are two types: even parity, where the total number of ones including the parity bit must be even, and the second one is odd parity, where the total must be odd. And finally, the stop bits. Stop bits signal the end of the data packet. When sending these bits, the UART drives the transmission line from low to high voltage. Depending on the configuration, there might be 1.5 or 2 stop bits. Now moving to the next part, where we will see the steps of UART communication. So let's walk through the step-by-step process of UART communication. First, the transmitting UART devices receives data in parallel from the data bus. This is typically data from the CPU or microcontroller that needs to be sent to another device. Next, the transmitting UART adds a start bit, possibly a parity bit, and a stop bits to create the complete data frame. And then this entire packet is then sent serially, one bit at a time, from the transmitting UART to the receiving UART. On the other end, the receiving UART samples the data line at the pre-configured baud rate to capture 8 bit. Now, after receiving the complete data frame, the receiving UART discards the start bit, parity bit, and the stop bit, leaving just the data bits. Finally, it converts this serial data back into parallel format and transfers it to the data bus on the receiving end, completing the communication process. So like this data is being transmitted from the UART receiver transmitter to the receiver side. One of the important part of the UART communication protocol, that is oversampling technique. So here what happens, instead of sampling each bit once, the receiver samples each bit multiple times. So typically oversampling rates are like 8x, 16x or 32x. So I'm taking here example of 16x oversampling technique. So at 9600 baud rate. So here the receiver samples at 1,53,600 Hz. Okay, so its frequency will be like. So when ideal state transition to low start bit, the receiver begins counting. So when the counting will be 0, 1, 2 up to 8, it will sample at the middle bit, the start bit. So multiple samples are taken to confirm if it's a genuine start bit and not the noise. So if the majority of samples are low, it's considered a valid start bit. So after detecting the start bit, the receiver calculates the center point of each subsequent bit. So the 16x oversampling, so it samples the position 8, then moving forward for the first bit at the 24th position, because we will sample 16 more tick pulses to reach the first data bit, middle part, which will be at 24th, then followed by 40, 56 and so on. So this mitigates timing drift and phase differences. So for each bit, multiple samples are taken near the calculated center. The final bit value is determined by majority voting of these samples. So this provides robustness against momentary noise spikes. Okay. Now, at last, we will see the advantages and disadvantages of UART protocol. So like any other protocol, UART has its strength and limitations too. So let's review them. So starting with advantages. So UART is wonderfully simple, using only 2 wires for bidirectional communication. So no external clock signal is required, reducing its complexity here. So okay, and the next is the parity bit provides basic error checking compatibilities. Okay, so and the next will be the structure of the data packet is flexible as long as both sides are configured identically. So however, there are some disadvantages to consider too. The size of the data frame is limited to a maximum of 9 bits, so we cannot send the data more than 9 bits at one frame. And UART doesn't support multiple master slave communications systems like some other protocols do, like SPI have master slave configurations. And for reliable communication, the baud rates of each UART must be within 10% of the each other. Means we have the error percentage is plus minus 10% of the baud rate. And that concludes our exploration of UART protocol. I hope this video has given you a basic understanding of how UART works and its importance in embedded systems and VLSI design systems in serial communication. So if you found this information helpful, please like this video and subscribe to our channel for more similar content on VLSI design and verification and communication protocols. Thanks for watching, and we'll see you in the next video. Thank you.